this introduction and for calling me an old fart. Actually, I thought I had a really bad deal when Lennart invited me. Of course, it's a really good deal to get invited here, and I'm very happy to be here. But he gave me the title Basic Bioinformatics. I thought, oh fine, I can do that. I'll talk about search engines, I'll talk about quantification. This is Basic Bioinformatics. Turns out you already had a talk about search engines by nobody less than John Cottrell, which is, probably one of the world's most esteemed experts in the field. You've heard a lot about quantification. A lot of stuff was in Bruno's talk, a lot of stuff was in the nonlinear talk. So, I couldn't talk about these things anymore, so now I have to talk about everything else that is basic bioinformatics. So what's the first thing that comes up to me when I hear basic and informatics? It's assembly, right? So let's do a bit of assembly. This is the code you use when you program the CPU directly. And actually, this is a joke, of course, right? I'm not going to talk about it. This is not assembly, this is a computer game. This is the computer game I play in my free time. It's amazing, it's the best computer game I ever played. You write assembly in the computer game, and you try to make the most efficient possible solution to solve a stupid task with minimal stuff. This has taken over my holiday. Anyway. And my solution there was the most efficient solution on record. It's because it communicates with the internet, right? So anybody who plays that, you want a screenshot of that, it's good stuff. So before I start with my lecture, I think it's very important that people get educated in bioinformatics, because you will use a lot of bioinformatics. You will not do bioinformatics, but you will use the products of bioinformatics. And in order to use them right, you need to use this. You need to use your wetware. It's not easy. It's also not hard, but it's not trivial. You cannot just say, oh, I'll click these buttons in whatever search engine I use, and then I'll expect things to come out. You have to think about what you're doing. And for that, we have made an extensive series of tutorials that explain about just about anything, at least in identification right now. Quantification is coming up. And they're freely available on the website of my group. There's a link to tutorials, and then it says Bioinformatics for Proteomics, so you really can't miss. And then it has all of these different sections. This is the first section, peptide and protein identification, and then it has these different topics, and it really goes step by step through everything. And it has PDFs with all the documentation. How do you do the tutorials? It has the resources, so all the data you need to do the tutorial, and it has links to all the freely available tools that you can download to do the tutorial with. Plus, these tools are really not tutorial tools, they're serious research tools. So you also get all the tools, right, nicely organized in one place. Some of them are from my group, some of them are from other groups. And this is just to show you what these tutorials look like. We tend to think they're quite professionally made. We use them a lot in workshops around the world. And they have nice screenshots of what you should see on your screen when you do certain things. They explain everything really nicely. They use colors. They have tips. The tips can be about the software, but they can also be about your research. And most importantly of all, they have these italics sections. And the sections in italics are questions. Every question is numbered. This is question 1.4. And these questions go from very easy to very, very hard. Some of these questions we don't know the real answer to, but we can give you some hints. And these questions are really there to make you think about what you're doing. And the really nice thing is that we went to the effort of providing a separate document with all the answers. And the document is, if I recall correctly, 28 pages, because some of the questions require a multi-page answer, because they go deep. That's why they're numbered. So if you want to learn about this, if you have a bit of time, it's worth actually picking up one or two of these, see if you like them, and maybe look at some of the other ones. They will really teach you a lot. Okay? So that's not the stuff I will talk about today. Instead, I'll talk about these things. First thing is FDR estimation. You all should be familiar with the fact that when you identify spectra, you match them to peptides. Some of the times you identify something wrong. Okay? And the problem is that we cannot get rid of them easily. So what we do is we accept a certain amount of crap in our results. And the amount of crap we accept is estimated by this false discovery rate, the amount of crap in your data. So this has been a very hot topic, not the topic of the day, although it's definitely very much in vogue again today, but the past 4,000 days. So let's say give or take 10 years and a bit, right? This came up when proteomics became high throughput. Then we started realizing we have to control for this. The problem is, how do you know that these FDR estimations that everybody uses work? So we'll talk about that, about a way to figure out whether they work, and I'll show you where they don't work. Then I'll tell you why this is going to get only more difficult as we go along. So in bioinformatics, we're reaching an impasse. The technology that we've been using for the past 10 years to make sense of our data is quickly becoming outdated. And I'll show you why that is in detail. And it's for specific purposes that it becomes outdated. So it's pretty much at the cutting edge now, but in 5 years, this will be standard. I'll talk a little bit about data management and dissemination because I spent a lot of time and effort during my career in this kind of stuff. I'll talk about quality control. I think it's the next big bioinformatics user-oriented challenge is to deliver quality control to people in proteomics. Talk about that. And then finally, I'll talk about some philosophical nonsense about bioinformatics beyond the algorithms and into the world of the bioinformatician. So, FDR estimation. I usually use this amusing little picture that some of you may find familiar to explain what the problem is with identifying peptides. It's not a perfect analogy, but it works reasonably well. You have to find Waldo, or Wally, depending on where you are in the world. And you know Wally has this white t-shirt with red stripes, and you know, he's a funny character. And so what you do when you go through this is you check everyone and you see whether they match the mental image of Waldo. And of course they put some decoys in there. Look, here's a decoy, there's a decoy, here's a decoy, there's a decoy. Here's somebody photoshopped themselves in as a decoy. That's what you get when you find things on the internet. And so the idea is that you actually try and match, and the pattern has to match correctly, right? And so the number of times you return a match that is wrong, you find not Wally, but somebody who looks like Wally, you count it as a false positive, this kind of thing, right? But hopefully, most of the time, you will find Wally who's hiding here, behind the old lady. And so, that works reasonably well. The problem is when we go to bigger databases, okay? When we go to bigger databases, it gets very, very difficult to make sure you've got the right guy. And that is what I will talk about, this problem. Where do you encounter it? Metaproteomics. You want to do proteomes of entire microbial communities. It's booming quite a bit. Second thing, proteogenomics. Everybody wants to do proteogenomics, right? But then you have your 6 reading frame translation of your genome database. This is a giant, giant database. Anything that is multi-species, right, is going to give you a lot of problems. So, we came up with a way to figure out what the problems are when you look at FDR. And we used Pirococcus furiosus, which is a really strange animal that lives at the bottom of the ocean, at these hydrothermal vents, these volcanoes at the bottom of the sea. And so these guys, they are very happy at 93 to 100 degrees centigrade. You take any of your cells, you put them at 100 degrees centigrade, everything is dead immediately. These guys are very happy. You know that they are happy because they're called Pirococcus, Piro for fire, Coccus because they're cocky, and Furiosus because they breed like crazy. So they must be happy. Yeah? Now they're a very special kind of archaeobacterium, an extremophile and extremothermophile. And there are these thermococci, which is a family. Now, if you look at the proteome of Pirococcus, it has a lot of proteins that we have as well. And if you go through the proteome and you look at the peptides, they actually seem to distribute in a lot of metrics like human peptides. But the sequences are dramatically different. In fact, here is the overlap. The shared tryptic peptides between human and Pirococcus are shown here. There are 5. All 5 of which are shorter than 6 amino acids, which are usually excluded from search results. So Pirococcus does not look like us. Although the peptides, when you look at how they distribute over a chromatographic run, if you look at the mass distributions, they look like ours. Now, why do we use this? We use this as an entrapment database. And the idea is simple. You search data against a human database. Of course, this is human data, HeLa data, and we get 8,000 PSMs identified. Okay? Now, we also do a decoy search. You know about decoy searching. So this is the number of decoys, which turns out to be 1% of that. Okay? That's the way we do this. Now, the question is, since we haven't told the search engine that we've included Pirococcus data, any Pirococcus hit must be wrong. Because we search human data against the Pirococcus database, everything we get back must be wrong. So we find out how many peptides did we match against Pirococcus, and that's the entrapment hits. And they should be lower or equal to the number of decoy hits. Okay? Let's go through that again. Decoys mean if I get 10 decoys out of 100 total hits, The 10 decoys are a model for 10 wrong hits in the real search. So I've got 10 out of 100 that are wrong. So my crap is 10%, 10 out of 100. If I now use Pirococcus in parallel, since I am sure that my FDR is 10%, I should not get more than 10 Pirococcus hits. Because if I get 50 Pirococcus hits, which are all wrong, I know they're all wrong, they're just a different type of decoy, now I suddenly have 50% FDR and my original estimate is wrong. Yeah? So I use Pirococcus to validate. That's the secondary decoy search. And you see that this works, right? You see that the amount of Pirococcus hits is always lower than what you would expect from the hits. But notice that we're doing something. Here we include Homo sapiens, which is about this size database. Here we include all Mammalia, which is this size database, 10 times bigger. Here we include all Vertebrata, which is yet another 10-fold bigger. And here we include all Eukaryota. And notice the overlap between all possible Eukaryota that we've ever gotten sequences from and Pirococcus is absolutely minimal. Right? There is practically no overlap. And you see what happens? We control this FDR beautifully. Right? So when the algorithms claim that your FDR is 1%, it really is 1%. So who can spot the problem here? What is the problem? There's a very, very big, shining, glaring problem screaming at you. Look at the green bar. From that side to that side, what does the green bar do? It goes down. You see that? The number of hits you get back goes from 8,000, 7,000, 6,200, and here, when the database really gets very big, it goes down to 5,000. Is this good? Do we like this? No. Okay? This is the biggest problem when you search a large database. The recall, the number of peptides you identify, goes down dramatically. Okay? However, we do still control the FDR. Yeah? Now, people have tried to fix that. So, for one thing, you can try and use a better search engine. So we tested 3 search engines. We used Mascot, of course, everybody uses Mascot. We use OMSA, which is known as a very conservative search engine. It doesn't give you many results, but it tends to have good control of FDR. And we use Xtandem, which typically gives you more hits. And then what we do is we plot the number of decoys against the number of target hits. So at any point you can calculate the FDR for that point by taking this and dividing it by that. So the thing is, you see here this line. For Mascot and OMSA, they follow that really nicely. And this is exactly what you expect. They're precisely at the place where we expect them to be. Okay? They give you the right number of hits. But if you look at here, sorry, this is entrapment hits. So this is Pirococcus, this is decoy. So 1 Pirococcus for 1 decoy. So that's perfect, right? The Pirococcus hits match the decoy hits. So the thing works. For tandem, however, you see that you get, for 200 decoy hits, you get 300 Pirococcus hits. So now, what does that mean? If we think that we have 200 decoy hits, we actually get 300 wrong hits back. So what have we learned? Tandem is underestimating the FDR. It's telling us, based on target decoy, that you have 200 crap hits, but in fact, when we try it on something else, we get 300 crap hits. That's 50% increase, right? Now, this translates, if you look at the decoy hits that you get from tandem, this translates in more good hits. So these are the target hits. So at 1% FDR, whoa, you know, I want tandem. It gives me 6,200 hits instead of 5,000. You know, it must be amazing. Yeah? This is what you now see. And interestingly, Mascot and OMSA are very similar. Also note, I don't know if John's here actually. Maybe he's not here. That might be good. Excellent. So I can say these things and he will not shoot me or be embarrassed. But you say that Mascot is really built for 5% FDR. That was the original default threshold. Look at where it shines. Mascot shines at 5% FDR. It's optimized for that. It has always been. Yeah? Using Mascot at 1% FDR doesn't kill the algorithm, but it's better at 5%. It's an interesting observation, and it's something that kind of makes sense. So tandem gives you more. These two guys give you about the same thing. So why is tandem superior? The thing is, it's not. When we look at the entrapment rate, so now decoys are gone, and we just look at Pirococcus. But since they are a type of decoy, we can do FDR calculation based on Pirococcus. Where's tandem now? oh look, it's at exactly the same place as where mascot is. I mean, it nearly tracks the curve perfectly. OMSA is still pessimistic, okay, but that's expected. So when we use Pyrococcus, suddenly tandem isn't special anymore, right? So what you get is the algorithm that gives you the biggest return is somehow exploiting something about the decoys that fails if you give it a real biological sample as an entrapment. And so we have a way now to calculate whether FDRs that are estimated make sense. It's not a perfect way, but we can already show that tandem has an issue here. Okay? Now, the big database, metaproteomics. We have OMSA in gray, tandem in blue, and the combination of the two search engines in orange. Combinations of search engines give you more hits. That's why our tools that are in the tutorials, Search GUI and Peptide Shaker, Search GUI ships with 7 free search engines built in. You download the file, you unzip it, you have just installed 7 search engines on your computer. And you run it, and you give the result to Peptide Shaker, it piles it all together, and it gives you this orange line, which is always better. It's usually not huge, it's 5 to 7 to 10% in best cases, but it helps. Now, as we've seen before, tandem outperforms OMSA. No surprises, everybody knows this, okay? Now, this is the normal Pyrococcus database, and what we're doing now is we're doing the inverse of what we did before. We're taking Pyrococcus data, and we're searching it against the Pyrococcus database. So we're identifying Pyrococcus proteins. This is data that comes from QExactive, so it's high MS resolution. This is the best data we can have right now. So, you know, Pyrococcus, we identify a lot of Pyrococcus proteins, everybody's happy, Xtandem does better than OMSA. Now, you see these dotted lines here, they're this strange thing, they're a new database. So, still Pyrococcus spectra. Now we search them against the Pyrococcus database plus the human intestinal metaproteome database. It's based on next generation sequencing of human fecal samples. And they took all of the open reading frames they could get from that and shoved them into a ginormous database full of bacterial sequences. And these bacteria look very different from Pyrococcus. I would hope your intestines are not 100 degrees centigrade, even if you ate the chili pepper. And so the point is, this database is enormous, and as expected, the blue and the gray line drop. But you notice one thing that you should have already expected. Tandem drops much more than OMSA. In fact, tandem and OMSA are now cut on the same size. That's because some of the tricks that tandem, unwittingly, it's not done on purpose, some of the tricks that tandem uses are now useless. Still, however, you do get an increase, and the increase becomes bigger than before, relatively speaking, when you use multiple search engines. So take home message number 1. Search engine behavior depends on the size of the database. In general. The big exception is MSGF+. Second, the harder the task gets, the more benefit you get from multiple search engines. Okay? So teamwork matters when it gets hard. But the problem, of course, remains that this is very unsettling. We go from, at 1% FDR, we go from roughly 9,800 to 4,500 hits. That's half of the stuff, poof. It's really, really annoying. And it's just because we changed the database. So people come up with a way to fix that. And the way they fix that, the first thing I have to tell you is why do we lose all of these identifications? It's very simple. I have plotted the distribution of the decoy scores, these are in orange, and the normal Pyrococcus scores in blue. What do you see? The decoys all have low scores, and the Pyrococcus have both low scores and high scores. And the FDR mechanism is you put a line here-ish, where all the stuff on the right has 1% orange compared to the blue. That's 1% FDR in the stupid way, okay? Now, this is a bit strange. Why does all the decoy look like that? Well, you know, the standard argument is it's because it's a good scoring algorithm. It can differentiate crap from real hits, and it seems to do so. When we go to the big database, the one with the intestinal metaproteome, look at what happens to the decoy scores. I mean, they move from about 18 to about 30. The decoy hits suddenly all get bigger scores. So why is that? why does the decoy distribution shift? It shifts because you now have, instead of, I don't know, 5,000 proteins, now we have the equivalent of, say, 120,000 proteins. Imagine the number of different sequences in all of these proteins. So the sequence space is now enormous. When you make shuffled or reversed versions of this sequence space, you will find a lot of sequences that start giving you better hits than before. There's a lot more sequence diversity that gives you higher scores, and the algorithms are not built to compensate for that. Now, there's another effect that you should notice. That is that this blue curve, it actually goes up dramatically. You see that difference? You know, it gets boosted, especially here. And the reason why it gets boosted is because it gets a lot more crap hits as well, that's here. But it also gets more good hits. Or so we think, because keep in mind that we're searching Pyrococcus data against prokaryotic organisms. The hits that we get are most likely false. So any increase in the blue curve is wrong. So this is not a good picture, right? So we make our FDR tougher, and whatever gains we have, we should not trust probably. In this particular case, right? Now, people fix that, and they say, yeah, but we can fix that. And the way we fix that is we pretend not to have a big database. So we first search against Pyrococcus, and then everything that's identified we put away. Everything that's not identified, we now search against the human intestinal metaproteome database. And that is called a two-stage search or a multi-stage search. And it's being recommended as a solution for proteogenomics by Alexei Neshvishky in Nature Methods most recently in his very nice review. And it's being suggested in a lot of papers as a fix for metaproteomics. So, let's see if it works. This was before Pyrococcus alone. This is what we showed, Pyrococcus plus HIM-PDB, so it gets this problem. And this is what happens when you do this two-stage thing. It's magic. Okay? This decoy distribution goes back to where it belongs. It's a little bit bigger, but it really doesn't make that much of a difference. And still, we get the blue curve from this guy. This is the best of both worlds, right? We take the good curve here, and we take the good curve here, and we make a new thing out of it. Problem solved. Until you do the math. We cut off first at 1% FDR. At 1% FDR, when we search the Pyrococcus database, we get 10,000 odd hits, and this is 100% from Pyrococcus. Of course, it's the Pyrococcus database, right? So here, the peptides, so this is peptide to spectrum match, this is peptides. We don't talk about proteins, that's too difficult. You get up to 100%, that's all fine. When you take this bigger database, and that is here, we get half the hits, remember? We halve the number of hits, but 99.4% comes from Pyrococcus. Our false discovery rate is under control. Everything works as we expect it to. At the peptide level, you go a bit over the 1%. Here you stay a bit under the 1%. That is rather typical. Any step you go up from the peptide to the spectrum, you tend to accumulate more FDR than you expect. At the protein level, there's even balloons. So, what happens in the two-step? We nearly completely rescue the identification count. Okay? So we go back to our 10,000 identifications. But 91.5% only comes from Pyrococcus. So we have 8.5% false discovery rate. Okay? We asked for 1%. We underestimate eightfold our FDR. At the peptide level, this is peptides, we're not talking proteins yet, this is now 20% FDR. Because a lot of these hits, these 8%, they are scattered randomly across all possible peptides. They're not multiple spectra against the same peptide. So this problem balloons at the peptide level. That's pretty dramatic. So have we done any magic? Yes, it's black magic and it took our soul with it. At 5% FDR, things are exactly the same. We control the FDR by sacrificing a lot of hits. But when we do the two-stage search, here it goes off the rails, there it explodes in your face. This is 60% is right, 40% is wrong. And people publish and they say, I did this, and I've got 5% FDR. And it's not their fault, right? It's not their fault. But now we can see that this creates problems. So this multi-stage searching thing, this is a deal with the devil. I'm inspired by the Catholics around us. So you really have to watch out for that. And you know what the biggest problem of all is? I don't have a solution for you right now. I mean, a few people in the world are working on solutions, but few people realize the problem, despite the fact that it's in plain sight. Everybody can do these analyses. You can do them in an afternoon on any data set you want. But the problem is, it's very, very hard to fix this, and we probably have to rethink the way we do our searches. So if there are any bioinformaticians in the room, raise hands. 1, 2, 3, 4. Wow, we're incredibly represented. So you guys have work to do. You want to do some work? This is a very interesting problem. So, now there's lots of Waldos. And that is the problem. So let's go into the problem in a bit more detail so that you understand and that I can give you a second thing that's on our very close horizon that will make our life difficult. It's the reason why FDR estimations fail in these big databases and in a lot of other cases. This is target decoy searching. Which of the following two pictures is Michael Jackson? Is this hard? You have a target and you have a decoy. Okay? Now we make the database bigger. Which of these is Michael Jackson? Right? Now you start to doubt, right? Is this guy on the left really Michael Jackson? Do you want to know what the answer is, where the real Michael Jackson is? You want to know? He's not on the slide. These are all imitators. Okay? This guy happens to be the best imitator, apparently. But so, the thing is, it becomes incredibly difficult to see the difference between things that look alike. And the bigger the database is, the more chances you have of finding multiple peptides that look alike. Now let me demonstrate how bad this problem can go by making a hyperbole. I'm going to do something extreme, like the rafting, but then worse. It's like I would be rafting on, I don't know, on a piece of paper, right? So I'm going to do something super extreme just to show you how bad it can get. You take a bunch of peptides. We took 70,000 identified peptides that we validated in a lot of ways based on their fragmentation patterns. These are beautiful spectra. Yeah? And then these 70,000 peptides, we started making these photoshopped versions, these imitators. So we permute some of the amino acids. That's a stupid trick. You switch them around in location, and you can do that across the whole sequence. But they stay isobaric. You do isobaric mutations. F and Q together have a roughly similar weight as a methionine oxidation and a lysine. This is actually ion trap data that we use for this. So, an ion trap cannot see the difference between these guys. Here we have deletion or mutation. Alanine and glycine together have roughly the same mass, at least for an ion trap, as a lysine. And then here we take asparagine and replace it with 2 glycines. So you see we make a lot of Photoshop peptides. This is always the same guy, but it yields very many Photoshop versions. So if this is our peptide, we make these Photoshop versions. Then we take another celebrity and we take all the other imitators. And so we go on so that every of these 70,000 peptides has at least 100 imitators in the database. This is really pushing the search engine, right? Because now the search engine is really, really confused. And you see what happens. This is the decoy distribution. Incidentally, we took a reverse decoy in yellow, and we took 10 different shuffled versions of a target database as a decoy in green. Do you see any difference between the decoys? So the next time somebody tries to publish a paper where they say reversed or 0. so many % better than shuffled, you go, bleh. Because even if you shuffle the damn thing 10 times, it gives you more or less exactly the same distribution. Okay? So how you make the decoy doesn't matter. This is the real hits in red, the original forward ones, and in blue you see the hits we get against our photoshopped peptides. It has shifted to the right. This is very scary. This is mascot. To show you that this is not a mascot problem, we did it for tandem as well. Does everybody see the strange pattern in tandem? So tandem has this discretization in the score. Yeah? It comes from the formula of the hyperscore. So it's quite funny to see the sawtooth, which you don't have in mascot. Although, if you look very carefully, there's a little bit of sawtooth pattern there. It has to do with the peptide length that is variable. Okay. What does that mean? This is a distribution of the ion score difference. I'm using mascot, but tandem gives you exactly the same. The ion score difference. So I take the spectrum, I take the original peptide hit, which I know is, 90%, 95, 99% right, and I calculate the score, and then I take the score of the best decoy hit. Now, if you look at the traditional shuffled or reverse databases, the decoy is nearly always worse than the original hit, okay? Except for this very small amount, which is our 1% FDR, okay? This is the 1% where the decoy actually gets a better hit. This is exactly what you expect. When you look at our Photoshop peptides, nearly all of them give a better hit than the original one. And it's very dramatic. 95% of cases, you get a photoshopped, you get an imitator peptide that actually gets a better score or equal score than the forward. And 75% get a better score and 20% get an equal score. This means that if you give me any of your data sets, any one you please, and you give me a little bit of time to create imitators, I will give you back your data set and I will say for 95% of your identifications, I have an equal or better match. Right? Oops. Now, this is of course a highly artificial situation. It's the biggest problem you can give a search engine. But what we wanted to show is that if you give them this problem, they break. Now, to be honest, this is now I'm getting into the detail, to be honest, they don't break that dramatically. If I show you 100 Photoshop pictures of someone and the original, what is your chance of getting the right one? I mean, you cannot tell the difference anymore. So what is your chance of getting the right one? 1 out of 101, right? Because you're randomly going to pick a picture. The search engine gets at least 100 decoys, at least 100 imitators for each peptide. So by random chance, 99% of the decoys should be better. But it's only 95%. So to be honest, we pushed these guys to the edge and they kind of hung on by their fingertips for a few seconds. Which is not bad, it's not bad. But it's not enough. This is the same visualization of how the score is distributed, but it's not that important. Now, we have tools like Percolator. Who knows about Percolator? Did John talk about Percolator? He should, because it's built into Mascot. It's really, really good. You want the search engine to beat today, it's Mascot plus Percolator. It's extremely good. And so, Percolator looks at all these features, right? Has he talked about that, features? We have all these features. So you can look at the mass difference of each of the fragment ions. You can look at the ion intensity and the B ions and the Y ions. You can look at how many B ions, how many Y ions. And if you look at all of these things, maybe you will find a pattern. For instance, decoys tend to have fewer Y ions, but more B ions than target hits. And so it learns, it adapts to that, and it figures out how things are different. So we try to find whether there's a way that we could use this approach to differentiate between the different hits. You see the decoys, the original decoys here, and you can see that the ppm mass error is indeed much bigger for most of these traditional decoy hits. So we can learn something from this. We can learn about the decoys. But now look at our directed decoys, the Photoshop guys. There is a difference, but it's minimal. And then here, this is the distribution of the MSMS error median. Okay? That distribution again shows a clear bias for these traditional decoys. It does not do that for the Photoshop peptides. Here too, this is the B ion coverage. Look at the massive difference that you get for these shuffled or reversed sequences. Look at the almost perfect overlap between the Photoshop ones and the original ones. None of these parameters is helping us. There's only one parameter that we could find that gives us a bit of an edge, and it's the arcane interquartile distribution on the MSMS mass error. It's the consistency with which the error moves in MSMS spectrum. And this is in an ion trap. And what you can see is that, well, the traditional decoys are much worse. Here, by the way, there is one shuffled guy that is very strange. You see the original one and you see the Photoshopped ones, and the Photoshopped ones are different. That's the only thing we could find. Okay? So there's a lot of work to be done here to fix this problem, because this problem, you don't notice it when you search human. You don't find it when you search yeast. You don't find it when you search E. coli. But you find it when you search yeast with 15 modifications, variable ones. You find it when you do a proteogenomics study. You find this when you do a meta-proteomics study. Not to this extent, not that bad, but you see the tail of this thing, which you have seen in the previous slides. And that is a problem that we currently cannot fix very well. Why do I make such a big fuss about that? Is because everybody's going into RNA sequencing, and they all want to do RNA sequencing data into a proteomics pipeline for matching the spectra. So what do people do? They take the reference proteome, they take the sequences that they get from the sequencing, and they add in the sequences that are not in the reference. And these are all small mutations of existing peptides. And now you're creating a database that looks surprisingly, although only fractionally, but surprisingly like this one. And we've been doing this with a group in Ghent, and what we see is that our identification rates in the combined databases go because of this problem. So this is really very close on our horizon, and it's a completely ignored problem. And the target decoy approach does not compensate for this at all. The target decoy approach is Picasso's cubist picture against the normal peptide. And now we have lots of normal-looking peptides that all look alike. We need new tools, we need new stuff here. Yeah? So it's not a happy message unless you're a bioinformatician. Good, talk about something else. Everybody knows this picture, right? It's the Great Wave of Kanagawa by Hokusai. And I think it's a beautiful metaphor for our life in the omics fields. Because this is high-throughput omics data. This is classical bioscience. It's the rock in the background, right? It's the one gene, one protein, one PhD in biochemistry style of things, where everything is under control. And this is all of us. So, how do we deal with this? What do we do? You can see this as a threat. You can also see this as an opportunity. So, the thing is, manage your data. How many groups, how many people here know of a systematic database-driven storage of data in the mass spectrometry group they are in or they work with? So how many people store their data in a database of some sort? Yeah, I know you guys do. You guys were pioneers. I think you guys beat even me to this, which is highly unfortunate. You see, nobody does that. So step back, think about this. Does that make sense? I mean, Facebook keeps track of every photo you take from your behind, right? And you don't even bother taking care of your proteomics data? Does that actually make any sense? It does not, okay? So a lot of people build tools for this, and unfortunately not all of these tools are universally applicable, and not all of these tools are very production grade. So we have one, which has been around since 2003. So I think Cellzone beat me, right? You guys had one in 2002? Yeah. And so, sorry? No, of course not, of course not. Well, look when I published mine, right? I waited until it was stable. It's still running, we keep updating this system, and apart from the Cellzone one, it's the longest running database in proteomics. The systems that exist were reviewed in 2010. There's a few new interesting ones that are possibly coming out in the near future. So keep your eye out for this, but really you should seriously consider, especially you young people who know about big data and what everybody tracks of you, to at least track your own stuff, right? I mean, seriously consider doing this. Yeah? Okay, why would you do this? I was in South Africa teaching a course with Catherine Lilly, and Catherine Lilly said, yes, and this peptide is very interesting because it contains my initials, Catherine S. Lilly, KSL. And there are very few peptides with KSL, so I make a VPN connection to Ghent quickly. I do one query on my database, and I say, oh, Catherine, this is through time, all of the peptides we have ever found that contain KSL, cumulative, and the number of spectra in each of the different runs in which we found it. And I got that like that, okay? This is a whimsical example. It doesn't make much sense. But it allows us to do so much stuff. We can data mine this stuff, you know, in myriad ways. Plus, it's super convenient for a lot of research purposes. And, you know, the most convenient thing is the biologist comes back after 2 years and says, oh, I'm going to publish this study now. Can I have all my peptides again? I don't know. There you go. And the other thing is that it allows you to take your data and chuck them into a public archive. Which again, it's the big version of what I've just talked about. And these public archives are super useful, right? You can do a lot of stuff with that. And so one of them is Pride, is the one I built at TBI. And it's part of a big consortium called Proteomics Change that tries to exchange data as broadly and as widely as possible and make life easy for you by making very complicated diagrams. But mostly it has these submit data and access data links, and they have this tool to submit your data. And it depends on whether you want to do a good job or whether you want to do a half-assed job. May I recommend that you try to do a good job? It will take about 1 day of your life to do a really good job. 1 day, which is peanuts compared to all the other time you're going to spend on getting your data published or acquired. Okay? But it will cost you 1 day to do it nice. But then everybody can make good use of your data, whereas if you do this, everybody else can just kind of, do something with it. Okay? Now, I'm not going to talk too much about that, just tell you that it's there. A lot of journals mandate that you deposit your data. You can keep it private during the review process, although the reviewers and the editors, you can give them a login and they can see your data, but nobody else can. And when it's published, a lot of journals automatically notify the database and it becomes publicly available. A lot of funders are asking you that these days, so please consider these kind of things and please spend the 1 day to annotate your data. If for nothing else, then for my eternal gratitude. Long story short, remember the tsunami? What if we could take this flood of data and, channel it and use it to irrigate the desert of the unknown proteomes that we have all around us, right? This is the vision, this is what it should become. This is in Qatar, by the way. And it's desalinated water, so the metaphor works, it's seawater. Right. Quality control. I always try to use, I'm using pictures, especially at long lectures like this. And I was Googling and I found this website, Epic Fail. I recommend it. When you feel really sad and really bad, go to this website. They have all these pictures where this is what we tried to do, and this is what came out. This one was one of the best. It's almost a horror movie. So people are trying to make peppermint icicles, right? So you make some dough kind thing, you turn it, you put a line. It's almost like making sushi, but then with a twist, literally. And then you twist it and you cut it into strands. And then people put their epic fail pictures. This is what they came up with. That is the stuff of horror movies, okay? So, the question now is, when you set out to do a proteomics experiment, this is your target. Do you know whether you ended up with this? It's a very important question to ask yourself, right? So in a lot of analytical fields, quality control is implicit, to the point that in analytical chemistry, which is our sibling field, they have something called accreditation. If you want to be an analytical chemical lab with an official accreditation that you're allowed to do this kind of stuff, you know what they do? They send you test samples on the stuff you're accredited for. This is made by the standardization organizations, and you know nothing, only that you're supposed to measure a particular compound or set of compounds in this mystery sample. And they ask you for the amount and the error on the measurement. And the error must be less than what they dictate is the norm for accreditation. Now, suppose you get it right, okay, accreditation prolonged. You can be accredited for another 6 months or a year. But what if you get it wrong? They send you back, you got it wrong, try again, but that's all. They don't tell you whether you were up, down, too big, too small, they don't tell you anything. The second time, you know what happens when it fails? They take your beautiful accreditation, they tear it up, and you are out of business. That's how they do quality control. Now, you're very silent suddenly, because nobody can imagine doing this in proteomics. But seriously, why not? Right? And I think the biggest problem is because you don't believe in your data. You don't believe you can do anything like that. And the reason why you don't is because you don't know how good your data is or how bad. But I give you the benefit of the doubt. And I think actually it's true. I think a lot of these modern instruments and the good protocols that we have today, we deliver quite good data, all of us. But if you don't check, how will you ever know, right? Doubt is worse than whatever comes out in the end. So, what we did was to gouge the interest in quality control. We did a little poll. We did this at the MPC meeting in Utrecht, together with Bas van Breukelen. First thing we asked, we had 68 respondents that took 8 days to collect. And then it said, how would you describe yourself? And you see a lot of people are MS researchers, which is the most generic term. You have some management people, 1. You have some bioinformaticians, quite a few actually, 13. And you have some service users and some technicians. And we have 1 genius. Which I know firsthand is actually Bas van Breukelen. He put that in as a joke, and only he thought it was funny apparently, so he's the only one who clicked it. And you know, when you have 86 or 1%, it's one guy, right? I mean, Anyway. So then, do you already use quality control? Shockingly, 59% says no. Nothing. Again, silence. Shocking. Then, is it easy to obtain software to help you do this? And Bas originally on the poll had yes, no, and then I whimsically added, does such software exist? Oops. Oops. Now, interestingly, 48% say, does such software exist? But 41% say that, yes, we do quality control. So how does that rhyme, right? That doesn't, but of course you can do quality control without software, which is what a lot of people do. So, how important is quality control? This is the big kahuna. And we asked 4 different settings. How important is it for your work, for the comparison between runs in your own lab, or between projects, for comparison with other labs, and for comparison and for quality assessment of public data? Interestingly, you see a pattern. This looks a heck of a lot like this, and this looks a heck of a lot like that. Because intra and your is the same, and inter and everybody else is also the same. So people have a similar feeling, and this is not random answers. That's nice to see. But you see, the main trend is people feel it's quite important. Only few people say it's not important. And for public data and other people's data, we think it's more important than for our own data. What happened to this? A scientist is self-critical first. Okay. And if you look at the distributions, essentially across all these 4, they're essentially the same, right? You shouldn't have been in the biostatistics course to figure out that these are the same. So, another question is, how easy is it for you to look at QC data and to analyze QC data? And here you see a shift. You see that it's slightly easier to visualize than to analyze. Okay? Analyze means process the numbers. Visualize means make a few plots, look at some stuff. And a lot of vendor software allows you to look at some of the stuff, and some of the commercial software does as well. So people on average have an average feeling about how easy it is. But it's not easy enough. This should move to here, because then people would use it all the time. Right? Okay, let's have a brief history of some attempts at quality control in proteomics. I'll start with the one, I'm a co-author on this one, and I really don't like this. The reason why I don't like this is this table. I can show you the email fights I had with the principal authors, me and a few other bioinformaticians. This is a flawed representation. It gets huge amounts of citations though. This is the HUPO test sample study. They took a bunch of human proteins, chucked them in a sample, and told people, so this is like this accreditation sample. Nobody knew what was in there, but they were equimolar. And they shoved the sample at people with how many proteins? About 20-ish. And they said, analyze anything you can and give us back the results. Okay? So people analyzed and gave back the results. And now there is the test of how many of these did you get right. These are the different groups that participated, anonymous. And this is the different proteins. And a plus means you found it, and everything else means something was wrong. And now you see that a lot of these proteins are wrong. Look at these guys, you know. Screw-ups. Huh? These guys too, screw-ups. Now this is not helping. Now you look at this and you think, oh, everybody does it wrong. But you know what the problem is here? Protein inference. John told you about protein inference, right? If you look at the peptides that people matched, every group matched peptides from all the proteins. So they got the peptides right. What they got wrong is the assignment of the peptide to the exact right accession number. And the problem here is this is the NCBI non-redundant database, which is enormously redundant. It contains all known splice variants, it contains all ever detected immunoglobulins, it contains all X-ray diffraction constructs, which are completely artificial. It takes all truncated forms ever recorded of every protein. So it's very easy to match a peptide to the wrong accession number. And they scored on the accession number. So they're not testing mass spectrometry, they're testing protein inference, which we frankly suck at. Okay? So if you look at this table gives you completely the wrong picture. The only useful thing in this table is these TR entries, which is where Eric Deutsch, who analyzed this data in detail, he found out that there was a trypsinization problem. And that's a very easy quality control that everybody can do. Search your data with 0 miscleavages and search it with 3 miscleavages. and count how many peptides you get with multiple miscleavages. If you have many with 2 miscleavages, by usual standards, your protocol was bad. Okay? Your trypsinization went wrong. It's a super easy test to do. And you have the data anyway. A search takes only a few minutes. Anyway, this was an attempt. I think I should label it as an abortive attempt. Also, you probably have not heard of this, which says enough. This is something completely different, but I thought that was a step in the right direction. Xu and Freitas made this tool that you could plug into a thermal instrument with this before and after scan or run. And it actually did this quality control thing, very quick and dirty. And based on that, it would do a diagnosis report like systems nominal or systems not nominal. And in the latter case, it would shut down the instrument. Or rather, it would go into an endless loop and the instrument would forever be waiting for this program to return. And that way they could conserve precious sample. If during the middle of the night your instrument went bananas, it would not continue to inject the last milliliter of cerebrospinal fluid you wrested from the poor cancer patient, but it would leave the sample there so that the next morning you could fix the instrument and then conserve the precious sample. It's a very simple, very elegant application of quality control. But they didn't go beyond this simple thing about blocking the machine if it starts doing crazy stuff. So we have to wait for NIST to come into the game with the CPTAC study. And these, this is NIST, the National Institutes of Standards and Technology. They say how long a second lasts, right? These are serious people. And so they started looking at the workflow and they said, how can we measure quality at as many of these places from a single raw file? You need nothing but a single raw file. And they came up with all these metrics, some of which are redundant, and they started scanning this for all the CPTAC data. So out pops stuff like this, peptide identification. So how many peptides do you identify? Ooh, these guys are not doing as well as most of the other guys. You see that? But they're consistent. Chromatography, nah, something is wrong, right? I should have listened to Mike. So here, ion source, aha. You see what's going on here? These guys with few identifications, they have a problem with the charge ratios. So everybody else has a lot of this is the median M over Z of the precursor, it's something else. This is the ratio of 3 plus versus 2 plus, and this is the ratio of 4 plus versus 2 plus. So you see that these ratios drop. So something went wrong in the ionization. That's why they can't identify so much. So you've not only seen a problem that is consistent and hampering all runs, you've also diagnosed the reason. And then there's other stuff like dynamic sampling. You see that's a bit screwed up here. You see here the MS1 features and what they tell you, and you see that that is actually not too bad. And then here you see the MS2 features, and that too is not too bad. But these features are incredibly interesting, and they tell you a lot about a lot of stuff. The raw file tells you about your experiment. Even trypsinization is included, but unfortunately everybody did it right here, so you can't blame it. But this is cool. Yeah? This is something that everybody should have all the time, right? Now, let's go into a bit more detail. The problem is, the NIST stuff is hard to run. It's a bunch of Perl scripts that only work if you rotate your computer counterclockwise 7 times at midnight and then sacrifice a black cat. Right? So Dave Tapp then did this QAmeter implementation, which does everything that the NIST thing does, but it doesn't require the sacrifice of the cat. It does require the turning of the computer, unfortunately, because he has a lot of different tools that you have to somehow glue together. But they're applicable to everything and not just thermal. The NIST stuff was only thermal. And it actually uses standard formats and open software to give you all of these things and nice plots in R. So you see the same kind of thing we've seen before, but now plotted in R. So this was a very good step in the right direction. Meanwhile, Proteome software, the guys who make Scaffold, implemented this as a paid add-on into Scaffold. The problem is nobody wanted to pay for this. Why would you not want to pay for this? This is worth a lot of money. Anyway, they did not, and thank God, these guys now threw it in the open source domain. So we can take this code, and Bas van Breukelen is now working with them to get this code and to make a free tool out of it. So hopefully, this will soon be in everybody's lab. Now, another pipeline that does this kind of stuff is the OpenMS pipeline through Topaz or KNIME, if you know this kind of stuff. It's published here, these two things. And it also allows you to calculate all of the NIST metrics. And the way it outputs that is in a new thing in QCML. So that's just some technical nonsense about a format intended to be transparent and to act as a placeholder for your metrics. Now, what is interesting about QCML is that it's an XML format, but you really don't care about that. You won't even notice it. The thing just spits it out, and you can make beautiful reports in PDF and things automatically from that, so who cares what it looks like on the inside. But what is really important, and this is something I really pressed when we were building this, is that it had to have a database equivalent. This is a database schema. Why? Because you want to archive this stuff. You want to be able to look at quality control over the past 10 years. Not this run, but everything. Why? Because you can do this. This is the median mass error of an Orbitrap machine. It's very close to 0, which is where you expect it to be. It has an upper fence of 5 ppm, and it has a 95% confidence interval here. So it's very, very good. And then you have that. So immediately you see something is wrong, right? You want to be able to spot these things longitudinally. You want to assess what is standard performance. What does that look like? And is this standard performance or not? Is it acceptable or not? Okay? The problem with that is that you need to keep also track of metadata. You need to know what you have been doing. This is the same kind of data, median M over Z, over very many runs. This is many years of mass spectrometry that you're looking at. In Ghent we can do that. We have everything in the database. And what you can see is that the protocols, which all have different colors, have different outputs. Yeah? And it really depends on the protocol more than anything else. So the way that you do your experiments necessarily influences the way your data looks. So you need to keep track of this kind of stuff, otherwise your variance will be very big. Now you can set it for the yellow stuff, it should look like this, right? This is a different metric, and this is a much less useful metric, because for some of the experiments it's all over the place. Unless all of these experiments are complete crap. No? Now, before you start going through the papers from Ghent and thinking that they're all bad, this is actually a standard sample that they ran. So it's not a real proteomics sample. But it's different standards and different protocols. But wouldn't it be nice to have this kind of stuff? And wouldn't it be nice if you saw that things are actually very conserved? If that happens, your brain is going to make a click, and you're going to say, accreditation, bring it on. I am capable of doing this. I trust myself. We need that. You can also do it on public data. The big problem with public data is that it's extremely heterogeneous. It's done by different search engines, different ways, different submission tools. Everything looks different. So the way to compare things is to put them all to a common standard. So we built a tool for that called Pride ASAP that does that, puts everything on a common standard, and it allows you to look at the data. Incidentally, we spent 7 years building this thing, hence the whimsical name ASAP. It's automatic spectrum annotation pipeline, but it also has a different meaning. We spent 5 out of the 7 years compensating for the lack of metadata that people submit. This is the biggest problem with the data. It's because people are too lazy to invest the 1 day. My guys have to work 7 years to get all of that fixed in a reasonable way. To be honest, it's getting a lot better nowadays. People are really taking their responsibility, but emphasize again, keep the metadata. And you should be keeping the metadata anyway for this kind of stuff in the database that you have locally, that you should have anyway, right? You see how these things fit together? When we organize ourselves, we become a serious analytical domain, okay? Anyway. Now, you can go further than that. We went into the thermal log files. Your instrument drops log files about the state of the charge in every component of the mass spectrometer. It has a lot of measurement on the hardware. So we decided, why not look at the hardware? This is the capillary temperature. This is what you set. This is what is requested. The software also logs that. This is the real temperature. You see how this is like a fuzzy algorithm and the thing tries to compensate constantly when the temperature changes? That's what your thermostat would do as well. It's a normal thermostat reading. But if this were suddenly to go boop, 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 then there's something wrong with your thermostat. Or maybe somebody's blowing on your needle with very frosty breath or something, I don't know. But you see how this is useful? You see how you can get this tolerance interval and you can define as soon as this thing actually goes beyond, 2 times that, I'm going to sound the alarm. Yeah? Speaking of sounding the alarm, this is the watts power consumption of turbopump 4. You see this yellow line? This yellow line says, I heard a strange noise from the instrument. It's really true, this is actual data, right, from our collaborators in Mol. And this tool that we built, that is freely available, you can annotate your data. So you see here, there is an event, but it's yellow, so you can't read it. So there's a strange event. You know what this red line is? The turbo pump ate itself. It literally sucked a lot of components into it, and it just... The instrument, look at the power consumption. Oh, done. Okay? So, the instrument was under warranty. But you know, the thermal engineers don't use this data. When we ask them, do you guys actually look at the log files? Oh, no. Only when the problem has occurred, we look at the latest log file and see, oh yes, the power consumption is low. But imagine, you know, you want to do professional proteomics? Monitor your instruments. When you see this go up, shut it down, call the service guy, says fix it before it's broken. Right? Or you can see when your columns start to degrade. You can see when maybe this sensor is starting to degrade. Why don't we do that kind of stuff? Process control is part of engineering everywhere in the world. Again, we want to be serious, we have to do this kind of stuff. It's easy, even I can do it, right? And I don't even have a mouse pad. Right. So, also on the epic fail, I don't think this is an epic fail, I think this is brilliant. Right? So we may not be analytical chemistry yet, but there's no harm in trying. Yeah? Even if it involves a towel, you know, you can do it. Okay, last bit, philosophical bit. Stupid joke about bad software. Who of you has ever used freely available bioinformatics software? Raise hands. Okay. How many of these 8 people have ever used freely available, are happy with the free software that they used? That's less than half. How many of the... Okay, I stop here. You see, this is the problem, right? If the software gives you the option to hang, crash, or start flashing, then it's not good, right? This is bad. How many people use commercial software? Everybody does, your instrument has it. But I mean, really use it, like Mascot or something like that. The rest don't use software? I mean, you either have free software or you have commercial software, people. You cannot have something in between. How many people use the software that ships with the machine? You may not think of that as commercial. Okay, probably everybody else. How many people are happy with their commercial or vendor solution? Right. Even less than people are happy with the free software, amazingly. But this is a problem. This is a really big problem in proteomics informatics and a few other fields, but mostly proteomics informatics, as far as I can see, is that a lot of the solutions we develop are not usable by other people. I speak as a bioinformatician. I try to not do that. But even we sometimes make stuff that could be better. And to be honest, I try to use tools from other groups as well. And this is sometimes extremely difficult, even for bioinformaticians, right? So, I want to make a few statements, if I may. Bioinformatician is a real job. And it should be treated as such, and not as the guy who sits there who's going to solve all my IT problems. You laugh because it's true. Huh? That's how people look at this. It's a sufficiently complex field that it requires a separate job title, that's bioinformatician. And it requires separate specialization. There are many courses around that now, although mostly are still very heavily genomics focused, and it's only getting worse with the sequencing. This, however, does not, in capitals, mean that you can treat bioinformatics as a black box, so you have to make sure you know what's going on, which is why we made these bloody tutorials in the first place. And if you look at the paper in which we published the tutorials, it says opening up the black box of proteomics informatics. If you go to somebody and you say, here's my raw file, I want an Excel sheet with a list of protein names, thank you very much, you are doing it wrong. You need to understand what happens to your data. Don't be the PhD student who stands there with me in the jury and goes, and then we identified 7,000 proteins. How? Ask that guy. It happens, huh? It happens a lot. So, commoditization. This means that the stuff becomes easy enough to use by yourself with a mouse on the screen. Commoditization is an ongoing process that we should learn to take advantage of. There's a lot of software out there that can help you. The problem is, not all of the software is very good, so we have to talk about that on the next slide. Typical analyses are not done in an afternoon. The bioinformatician is not a biomagician. Instead, it has become a substantial part of any project, and I would dare say, and we've heard this from the introduction by Henning, that our projects are becoming so complex that bioinformatics is now an integral part of your study, and in fact, a lot may depend on the bioinformatics. The bioinformatics, now I have to start to duck slightly, might be more important than the experimental part. For some of you, the experimental part is sufficiently standard in the terms of how you carry it out, that it's difficult to mess it up. But the bioinformatics might be very tricky. If you do not consider that, and if you assume that some kid down the hall is going to fix that for you in an afternoon, after you have done all your analyses, that is a very bad way of starting a modern proteomics experiment. You should think about these things. For that reason, I'm not the only idiot thinking that. Funders increasingly require data analysis and management plans. How many of you know of funders in your home country that ask you a section specifically, data management and analysis? So I know it's in the UK, I know it's in Belgium now, I'm not sure about Germany. Yeah? No? So it's coming. It will take a few years, but it's coming. Because people notice that a lot of projects fail because of that. People acquire enormous amounts of data and then they go, oops, what now? Yeah? So this is meant so that you think out whatever you want to do in your bioinformatics before you do the experiments, and that you budget it in your project so that it actually can be good. Finally, for full clarity, and this is extremely important, the bioinformatician is not there to fix your printer. The mass spectrometrist is not there to fix your bite. It's the same, okay? So stop treating these people like IT help desk people, because you know what happens to them? They get really frustrated, and they go to industry where they make 3 times more money. And I don't mean biotech industry, I mean everybody who needs a programmer these days, which is about anybody. I lose PhD students to Silicon Valley all the time, right? While they're doing their PhD, these guys go away. And if they're lucky, after 2 years, instead of a PhD, they will be multimillionaires. This is the challenge. So you want to treat these people reasonable. I don't say, you have to treat them like gods, but treat them reasonably, because otherwise you're chasing them away. When this happens, be careful. Right. Now, we've talked about help the poor bioinformatician. Now we talk about why the bioinformatician sucks. So, the commoditization of bioinformatics tools is haphazard at best. Why? Bioinformatics is too often an afterthought in the project. It's true. And it shows in the results of the bioinformatics efforts, because they're hacked. They have to be done quickly on no money. Bioinformatics is actually considered as irrelevant by many experimentalists because their focus is on getting the data. There's nothing wrong with that. Right? However, it does impact the ability to do a decent analysis if you don't care about what happens next. In rare, but highly unfortunate situations, bioinformatics solutions are considered competitive. And people say, we can do this amazing thing. I'm not going to show you. Yeah? Are there any heavy metal fans in the audience? Yeah? So you guys know this double tapping technique on the guitar that was invented by? No? One of the greatest metal guitarists of all time. Van Halen, Eddie Van Halen. When he invented it, he made these awesome solos. You know what the guy did when he performed them live? Turned his back on the audience. It's really true. So that nobody could see his secret technique. Don't be Eddie Van Halen, right? Imagine you go to somebody. I have this protocol that isolates every phosphopeptide in the sample, but I'm not going to show it to you. See, that doesn't make any sense. I give you bioinformatics, it's the same thing. It's part of your experimental protocol. Now, the development of really solutions for you guys in bioinformatics is heavily counter-incentivized. I will show you that. I will prove it to you. Companies provide some good solutions, but the problem with them is that the cutting-edge stuff tends to, drag a few years before they really make it into the commercial solutions. And the commercial solutions, when they have it, you have to pay extra to get the update usually. So, it takes a while before this spreads in the field. So free software buffers that. And many groups are constantly reinventing the bioinformatics wheel. Or rather, they are first figuring out that there is a substance called rubber. And then they're figuring out that you can vulcanize it. And then some clever guy says, I can build an inner tube. And maybe after that, they get to the wheel. Yeah? So we are, how many search engines are being built? Do we need all of them? Is any of them really better than the other ones? I would say we need 4 or 5 anyway, right? You need to scatter this a bit. And you need some innovative ones. But do we need the same old, same old? So why are we doing that, right? Anyway. This is my beautiful hand-drawn picture of why cost-benefit curves matter when you develop bioinformatics tools. This is the bioinformatician cost-benefit curve. This is how much time it takes to get a paper in bioinformatics with a hacked together Perl script or R code or whatever. Okay? You build a cool algorithm that does a cool job. It's easy. You get the paper. Big benefit. This is the amount of effort you have to do to get some extra citations for said paper. You know what this extra effort means? It means that another bioinformatician can run it. Okay? How often do you think this happens? I would say in about 50% of cases people go this far. Okay? Now, the cost-benefit curve levels off after that. Now we look at the user. This is the user. They don't care jack about the bioinformatics solution until it actually works. But look at the benefit is minimal. Because the problem is it doesn't work all the time. But if it works all the time, it gets a little bit better. And then it works all the time on all the cases you throw at it. And then it becomes really useful for you. Okay? This is not to scale. In order to get a piece of software developed that does this, you're looking at multi-year things. Remember my database that took me 7 years to publish? This is not atypical. I typically go about 3 years between making the tool available for free to everyone, including the source code, and publishing the damn thing. Because you want people to use it, you want to find the bugs, you want to fix the bugs, and you don't publish until it's finished. You don't publish a protocol that is half-assed, right? You do the same thing with software. You want, when people read it, that they can download it and use it. It's important. But the problem is, where's my incentive? Because I could have published it in bioinformatics and be done with it, right? So my science advisory board looks at this and they say, you're the biggest idiot we've ever seen. Because why are you doing this? You know, people think I'm a nice guy. But that is really the big problem. So the way to fix that is we have to incentivize this for the bioinformatician. Right now they have no incentive. So we're trying to work on that very hard to make it worthwhile for people to make better tools. And you will benefit as a result, and you don't have to do anything. You know? Just sit back and hope that we're successful in this. But that's a different thing, I don't want to talk about that. In order to help you, we recently published some guidelines in JPR, with this amusing picture that I photoshopped myself, about managing expectations, you know, a reality check for bioinformatics papers. And we came up with 3 different formats. Now in JPR, if you want to publish a bioinformatics research article or application note, it has to work. You have to say when it does not work. You have to say what you need to run it. You have to provide documentation for you, the user. You have to provide documentation for developers. You have to provide sample data so that it will run the first time. You will provide benchmark data so that other people can compare their performance against yours in the future. You have to provide availability, you have to provide a license, and you have to provide system requirements. This was shocking. This does not exist anywhere else. It was shocking that this did not exist. And when you don't want to do all of that, we call it a brief communication. The idea is that when you, a proteomics person, reads something like this in a proteomics journal and it says brief communication, you say, I don't bother. It could be cool, but I'm not going to go to the URL because this is not going to work for me. And that's the whole point. But when you see a research article or an application note, you say, I'm going to download this stuff and it's going to hopefully work for me. And the reviewers should check that. Okay? So we hope to, start by doing this and then do some positive incentives as well. Anyway, in conclusion, if the president can embrace coding, then you can. So, thanks.